Cosmic Orgasm presents to you Brown Dwarfs. How do stars form? Gravitational collapse in a nebula due to density perturbations can be caused due to nearby supernova explosions. The energy released from gravitational collapse is transformed into thermal and radiative energy. Half of the energy is radiated out, while half of it goes into increasing the thermal energy and hence temperature of the star. This is called the viral theorem of astrophysics. If enough energy is released from the gravitational collapse such that the temperature of the core of the mass reaches fusion temperature, then thermonuclear fusion starts. A star is born. Stars are the major creator of worlds. They synthesize several elements in the core which are blasted off into space by supernovae. These elements are accreted and form planets. These elements are essential for the formation of life forms and eventually intelligent beings like us humans. But what happens if this remarkable process of star formation just fails at the end step? What happens if the accreting mass forming the protostar releases gravitational energy which falls just short of the required thermal energy to produce a temperature for which thermonuclear fusion is sustainable? Then we get a brown dwarf. Prediction and discovery. Brown dwarfs were first predicted theoretically by Dr. Shiv S. Kumar. During the period of 1958 and 1962, he developed the theory of the very low mass gaseous objects that were unable to sustain hydrogen-burning thermonuclear reactions. This theory led to the prediction and subsequent discovery of the first true brown dwarf, which received the name Tidey 1. So, what are they? Well, they're not really brown, but astrophysicists are just bonkers.
When clouds of gas and dust contract gravitationally, stars form. The birth of star occurs when the fusion reaction of hydrogen into helium gas has ignited in the core. The key variable that determines the formation of the star is the accreting mass. The mass of the contracting cloud is below certain minimum value. Instead of star, a substellar object known as brown dwarf forms. But what is this minimum value of mass? It is found and it turns out to be around 0.07 and 0.08 solar mass. Let us take a look at heuristic derivation of minimum mass limit. Let us consider a protostar which is going to form has a mass capital M and radius r. The gravitational potential energy, as we know, is gm square by r. Now, if the protostar is composed by, let's say, np number of protons which has mass mp, it follows that m is equal to np times np, and thus substituting this value in our energy equation, and now our energy equation becomes energy is approximately gm np mp upon r. If we assume that the protostar is made up of ideal hydrogen gas that is completely ionized, then according to statistical physics, E is approximately n kBt, where kb is Boltzmann constant, n is total number of particles, and T is temperature. Now equating these two values of energy, we get is nkt is approximately gm np mp by r. Now cancelling n, as we have assumed that electrically neutral hydrogen gas where Ne is equal to Np is equal to n. Now we get is Kt is approximately equal to Gm Mp by R, and if the T is approximately equal to Tij, that is minimum temperature required for ignition of hydrogen to helium, and we put mass is approximately the minimum mass, that is minimum mass required for star formation, and then we get value of R, where R is approximately Gm minimum Mp by K Tij. Now replacing this R in the minimum mass equation which has been derived in this reference, and after algebraic manipulations we get minimum mass approximately h cat square k by g square me mp raised to 8 by 3 the whole raised to 3 by 4 times Tij raised to 3 by 4, which is approximately equal to 3.08 times 10 raised to 28 kg, which is approximately 0.016 of solar mass. The accepted value from a proper astrophysical calculation and consideration is 0.08 solar mass. Now let us study some physical properties and composition of these brown dwarfs. They have masses ranging from 13 times the mass of Jupiter to 0.07 times the solar mass, which is nearly 80 times the Jupiter mass. It's weird enough that adding more mass to these brown dwarfs just increases their density and not volume. The lighter ones, which are as light as 13 times the mass of Jupiter, can fuse deuterium, and heavier ones, which are 65 times the mass of Jupiter, can fuse lithium.
So how do we observe brown dwarfs? Most of them emit mostly in the infrared region and feebly in the visible end of the spectrum, rendering them quite dark to the visible spectrum. Warmer ones still emit some visible light. Those emitting visible light look magenta. But shouldn't they look red? Actually, methane and water vapor present in its atmosphere block more red light than blue, so we get an overall magenta color. Hence, brown dwarfs are not really brown. To the naked eye, they either appear dark or magenta. So this is an artist's rendition of a brown dwarf looking magenta. Some are so colder that with their discoveries, new classes of spectral classifications were made, namely LTY. And this is a mnemonic to remember that, oh be a fine girl and kiss me like that yeti. So Gliese 229b is the first class D brown dwarf which was discovered in 1994. Here you can see the Hubble spectrum of that, which shows no intensity in visible region and suddenly peaks in the infrared region. So Gliese 229b orbits the star Gliese 229, which makes it a binary system, and it is found in the constellation Lepus.
We are going to talk about high mass brown dwarfs versus low mass stars now. Brown dwarfs are distinguished from stars by lithium test. Recalling from class discussions that through the pp2 chain, stars utilize lithium in their cores to form helium. It turns out that they do so very early in their life cycle. On the other hand, brown dwarfs having masses near 65 Jupiter masses cannot fuse lithium. Hence, the presence of the lithium spectral line in a candidate brown dwarf is a strong indicator that it is indeed a substellar object. Some brown dwarfs contain atmospheric methane. The spectrum of Gliese 229b, a T-class brown dwarf, shows a spectral line corresponding to methane. Unlike stars, older brown dwarfs are sometimes cool enough that they, over very long periods of time, atmospheres can gather observable quantities of methane which cannot form in hotter objects. Some brown dwarfs also contain water vapor in their atmospheres. Here is a graph of the absorption spectrum of Gliese 229b. It is possible in brown dwarfs that through atmospheric convection, iron is transported across the dwarf. This phenomenon, not possible in small stars, is termed iron rain. We are going to talk about low mass brown dwarfs versus high mass planets. Brown dwarfs are roughly the same diameter as Jupiter. At the higher end of their masses, their volume is governed by electron degeneracy pressure, while at the lower end of their masses, Coulomb degeneracy pressure plays a dominant role, as it does in planets of high mass like Jupiter and Uranus. They emit mostly in the X-ray or infrared region of the spectrum. All warm dwarfs continue to glow tellingly in the red and infrared spectra until they cool to planet-like temperatures, which is under 1000 Kelvin. When is an astrophysical object considered a brown dwarf? According to the International Astronomical Union (IAU), an object is considered to be a brown dwarf if its mass is above 13 Jupiter masses, and anything below it is considered to be a planet. The limit to the mass a brown dwarf can have is considered to be 18 Jupiter masses, above which the object can sustain thermonuclear fusion and hence considered as a low mass star. There is, however, much debate regarding these demarcations. It is also debated whether brown dwarfs would be better defined by their formation process rather than by theoretical mass limits based on nuclear fusion reactions. Under this interpretation, brown dwarfs are those objects that represent the lowest mass products of the star formation process, while planets are objects formed in an accretion disk surrounding a star.
Recent developments. Estimates of brown dwarf populations in the solar neighborhood suggest that there may be as many as 6 stars for every brown dwarf. A more recent estimate from 2017 using the Young Massive Star Cluster RCW38 concluded that the Milky Way galaxy contains between 25 and 100 billion brown dwarfs. In a study published in August 2017, NASA's Spitzer Space Telescope monitored infrared brightness variations in brown dwarfs caused by cloud cover of variable thickness. The observations reveal large-scale waves propagating in the atmospheres of brown dwarfs, similar to the atmospheres of Neptune and other solar system giant planets. These atmospheric waves modulate the thickness of the clouds and propagate with different velocities, which is probably due to differential rotation. In August 2020, astronomers discovered 95 brown dwarfs near the Sun through the project Backyard Worlds Planet 9. Now is an animation of a brown dwarf floating in the vastness of Space.